So our goal today is really just to focus on use substitution specifically. And this first module, keep in mind what our goal is. Our goal is to try to figure out how many of these integrals we can solve by hand. And then we'll also talk about how we deal with the ones that we can't. So let's take a look. I got a few examples I want to go through for use substitution, and I'll talk about use substitution as I go through it. So first one, I have the antiderivative of e to the negative x. I'll point out a couple of things just because we're doing integrals together for the first time. For instance, notice there's no limits. That makes this an indefinite integral. And so the answer will be a family of functions. If you remember from Calc 1, you need the plus c when you have an indefinite integral, unless you're given some kind of initial condition. The next thing we would notice is we have more than just a basic antiderivative, right? One of our favorite functions in calculus is e to the x. Well, what's the antiderivative of e to the x? And when I ask questions, you can type in chat, perfect, or you can always turn on your mic and answer. So this is our favorite because this is the one function who is its own derivative and its own antiderivative. Now, because we have an indefinite integral, we put a plus c on there. Now, what we want to look at, though, is when we have more than just e to the x, like in this case, e to the negative x. If you remember back from your derivative rules, if we were taking the derivative of e to the negative x, it'd be a chain rule. So that means to do the antiderivative, we actually need to undo the chain rule. So use substitution is all about undoing the chain rule. I'm going to show you how I like to do it. I'm going to show you a couple different things from the notation as well as we go through this. And feel free to, if any questions arise, let me know. Like I said, I think the use substitution, judging by the scores on the lessons, you guys are pretty comfortable with this already. But I just want to show a few of the nuances and see what kind of questions might come out. So whenever you're doing use substitution, you'll have an inside and an outside function. Now, it may not always look like that. Maybe hard to tell what's inside and what's outside. Sometimes it's very easy. But think about what we're trying to do. We're trying to undo the chain rule. Well, the chain rule is when we have a composition of functions. So there's an inside and an outside. So I'm looking at this one. I know the negative x is what's making this not our basic antiderivative rule. So I'm going to let u equal e to the negative x. Now, excuse me, sorry. I'm going to let u equal negative x because it's just that exponent that's the issue. Now, I want to talk a little bit about what happens next. Our goal is to get all the x's out and get it all in terms of u. Once you choose u, then you calculate basically du dx, which is the derivative of u with respect to x, which is just -1. Now, a lot of times when we don't see it written this way, this dx gets cross-multiplied over here. And I normally won't write it this way either. You'll normally see me write it this way, -1 dx or negative dx. All right, I just wanted you to see where the dx notation comes from. Now, we're ready to make our substitution, but there's one thing that isn't in there. I have a dx in there, but I would need a negative dx. So I'm going to show you how I do it, but I'll also show you another way. So what I do is I say, oh, I need a negative dx in there. Well, I just changed my original to have a negative dx right there. So to make sure I compensate for that, I put a negative out front. So whatever I do inside to make my substitution work, I undo on the outside. We can always do that. by a constant. Because now I can make my substitutions. This negative x, well, that's u. And negative dx is du. And now we have a basic antiderivative. As you guys told me before, the derivative of e to the x is e to the x, so the antiderivative of e to the u is e to the u. It's an indefinite interval, so we need a plus c. Okay. Question for you guys. Are we done? And I know this seems trivial, but I want to make, I want to stress this point because as we get into other problems, we might be dealing with different variables than x and u. We might be looking at multiple techniques of integration in the same problem. So we want to pay attention to when we're done. We're not done. Our problem started in terms of x. We want to end in terms of x. So as John said, we want to sub back. U is negative x. So negative e to the negative x plus c. All right. Now, I want to show you one small variation of this that I know some people like to do, which is totally fine. All right. So you've got your e to the negative x dx. It's just, I use what I do in blue there. Let's just say, so we let u equal negative x, and then our du is negative dx. And then for the substitution part, what some people like to do is actually solve for dx. So, we divide both sides by a -1, and we get dx equals negative du. And sometimes this may feel like a little bit easier substitution route. So now when we sub, here goes our u in there. So e to the u. And what we'll do is we'll put a negative du in for this guy. Now we'll pull that negative out front. So negative e to the u du. And you can see we get the exact same thing. So I want you to do whatever you are most comfortable with. When I'm doing problems, examples, you'll see me do it like I do in the blue. I like to change what's in the integrand and compensate outside. But I know there's a lot of people who like to solve for the dx and do a direct substitution. Neither way is better or harder or worse than the other. So kind of user preference on that. I just wanted you to know that both ways are fine. Okay, let's go with a little bit more interesting example. That one was a little bit on the basic side. So we get a function like this. I think when there's something like this, it's pretty obvious what the inside is because it's under the radical. If that weren't so complicated, we could deal with this a lot easier. So I'm going to let my u equal the 2x squared plus 1. Now, when you're looking for your u, another thing that we need to make sure is that we can get the du in there. For example, if this x was not here, this would not be a u substitution problem because look what happens when I get my du. 4x dx, I'm just taking the derivative of u. Well, I need another x in there in order for this substitution to work. If this had been an x cubed, we probably wouldn't want to use u substitution. So we want to make sure that what we choose for u allows us to also to get du in there. Now, there's too many variations, obviously, for me to go through all of them. You saw some examples in the lessons. You're going to see some more examples in the homework. You're going to work on some more examples today. And you'll get used to it, choosing your u in a lot of different situations. Okay, now, like I said, I have my way of doing it. I know I need 4x dx in order to make this substitution work. So I need a 4 here. Well, I put in a 4, then I got to multiply by a 1/4 because I do not want to change what I have. So that's how that works the way that I like it. The other way of doing it, like I said, solve for dx, right? So dx would equal du over 4x, and then you do a straightforward substitution. All right, so there is my du. This is what I let be u. So I have 1/4. The 4x dx is du, and I end up with square root of u. Now, as a reminder, when we have a radical, we change this to be a fractional exponent. So 1/4 times, 1/4 the integral of u to the 1/2 du. And now we can do our antiderivative. And here's the way I like to think of the antiderivative of our power rule. Increase the power by 1, divide by the new exponent. So 1 over 3/2. There's my antiderivative. Now, one thing we never want to do is leave a fraction in a fraction. So we're going to clean this thing up a little bit. So 1/4, 1 over 3/2 is 2/3. U to the 3/2 plus c. And like you guys told me before, we're going to have to substitute back. We can also clean up this fraction a little bit. Both those are divisible by 2. So 1/2 times 1/3 is 1/6. And we put our u back in there. So 2x squared plus 1 to the 3/2 plus c. You do not need to rewrite that half fractional exponent as a radical. You could leave it as 3/2. In fact, I think this is easier. If you wanted to, you could say 1/6 square root of 2x squared plus 1 cubed plus c. But I think this is perfectly fine for this kind of problem. All right. How are we doing? Any questions on that? Excellent. Okay, we're going to do one more, and it's only because I want to do one that's a definite integral, because there's one thing that I want to show you that I like. Again, this is going to be a user preference thing, but I have a reason for liking it, and I will explain that here as we go through the problem. So right off the bat, you see limits, definite integral, meaning our final answer should be a number, as opposed to a family of functions like we got in the last two. And when I say a family of functions, that's what the plus c is doing. Because without the plus c, it's just a single unique function. But the plus c, every time I change c, I technically get a different function, but it has all the same characteristics of this function. Hence why we call it a family of functions. Definite integral, we should get a number. One of the nice things about definite integrals, we can do definite integrals with actually our graphing calculator. If you're not sure how to do that, send me an email and I can send you a video on how to do that. But it's nice for checking the answers. So let's go ahead and do this one by hand. We need the inside and outside. We need to find our u. And you know, a lot of times du will never go in the denominator. So looking at the denominator for u is a good place to start when we have a rational expression in our integral. So our u is going to be x squared plus 9. We can, once we have our u, we can calculate our du, 2x dx. And we can get to work on our substitution. Like before, I have an x dx, but I need 2x dx, so I'm going to put a 1/2 out here. And now I'm going to start to do my substitutions. So I got 1/2 There's my du right there. And this is up to you. You can write du on top, and then this is our u. Or some people like writing it this way, 1 over ud. Okay, those, oops, that should be a u, not a w. Those are the same, guys. Either way is totally fine, whatever you're more comfortable with. Now, here's where I would like to recommend this for you, but you do not have to do it. Now, 1 and 2, those are x values. That's x equals 1 and x equals 2. My integral is in terms of u now. So if I were to put 1 and 2 here, like so, that's technically not correct because those are u values and those are x values, but it should be u values. So what I like to do and what I like to recommend on definite integrals is changing the limits. Is it necessary? Absolutely not. And I'll talk about the alternative here in a second. But how you change the limits, well, here's your exchange between u and x. So when x is 1, so 1 squared plus 9. So for the limit of 1, where x is 1, u would be 10. And u equals 2 squared plus 9, or 13. So those are limits in terms of u. Reason I like doing it this way is because now I'm just working from here on down. So this could be put into the graphing calculator, for instance, or I don't have to worry about substituting back because I do see that mistake happen. Also, right now, u substitution is going to be our focus. Next week, when we get more techniques of integration, we might have a problem that needs several different techniques to solve. And this actually will simplify things because then we don't have to sub that. Again, not required because you can always just do it like we did the other problems and then sub back and then put in your limits 1 to 2. But this is just my recommendation. So we need another basic antiderivative. What's the antiderivative of 1 over u? Very nice. Natural log. Now, technically we do need the absolute value for the general antiderivative. The reason is because 1 over u is defined for all reals except 0. Natural log of u is only defined for positive numbers. So to make these actually match up, we use the absolute value. We don't need the absolute value in this one because we're going to be plugging in numbers that are already positive, but it's not going to make it wrong either. All right, so if you did put in the absolute value, that's not a problem. And then we have to put in our limits. So we put a line behind. This is just a little review of this notation. Notice the integral symbol turned into a line behind. This tells the reader that the antiderivative has been taken, but the limits haven't been plugged in yet. So we have 1/2 upper limit, so ln of 13 minus ln of 10. And guys, this is fine for a final answer. It's nice and exact. It's not a decimal approximation. If you want to get fancy, we can use some properties of logs. Subtraction of 2 logs, this should look familiar. ln of a minus ln of b equals ln of a over b. We can make this ln of 13 over 10 or ln of 1.3. These are the same answer, guys. More would accept this answer or this answer. So I'm not telling you have to do this, but for those of you guys who like playing around with properties of logs or like looking at answers that are equivalent, having the 1/2 out front If you remember, that can actually go up in the exponent of a log. So 13 over 10 raised to the 1/2 power, or ln of the square root of 13 over 10. Again, we were fine here. You guys are done here. Just a little, I had the opportunity to review some properties of logs, which will come in useful in some future problems. So I just wanted to take that opportunity. Notice our final answer is a number. This is nice and exact. One of the things I will stress in here is when possible, we love exact answers. All right. As soon as we turn this into a decimal, we have to round it off somewhere. We've introduced round off there. So whenever we can be exact, we try to be exact. All right. Okay. Questions about this? All right. Okay. Then we are about to break into groups. But there's something I want to show you because I don't know if everybody is aware of this site. Now, we've talked in here a little bit about Wolfram Alpha. We will use that on occasion. Desmos, we might use that every once in a while. But here's one that I don't know if everybody's seen, and it's called Symbolab. Okay, and it's just symbolab.com. Now, here's why I'm showing you this one. Notice all the math symbols. So let's go back to problem B. Let's go back to this one. All right, so we did the integral of x times the square root of 2x squared plus 1. There's our integral symbol, x, and then square root 2x squared plus 1 dx. And here is some of the steps of our integral, and check out what our final answer comes out to be. 1/6 times the quantity 2x squared plus 1 to the 3/2 plus c. Looks familiar, right? Right there. Now, I want to talk to you about why I'm showing this. Please realize that, you know, when it comes to the exams, the proctored exams, you will have to solve some of these integrals by hand. Not really, really complex ones, but ones kind of like the ones we looked at just now. But when you're doing homework, when you're working in groups, when you're doing problems for the take-home, Symbolab is a great tool for checking your answers. And what's really nice about it is the problem entry, because of this toolbar, and you can expand the toolbar, will allow you to put in the problem the way that you're seeing it. Okay. So when I wanted to show you this because we're about to break into groups, and you know, you're going to work on some integrals, and you might want to say, well, we got this answer, but we want to check and see if it's correct. Symbolab is a great way to do that, to make sure that you're getting the correct answer. And then if you're not, you can retry the problem. You can call me into your room, and I can take a look, and we can see where we might be having issues. Okay, so Symbolab is a great tool. I wanted to make sure that everybody is aware of it. We will get some opportunities to use Wolfram Alpha, and probably try and use Desmos once or twice. We're not doing any graphing right now. Maybe next week or the week after we will. But Symbolab is one I wanted to show you because we're about to go into groups, and it's one you could use to check your answers. Okay, but I don't want you to become overly reliant. Think of Symbolab as a way to check your answers, but not a way to do your homework. You do your homework, use Symbolab to help you out. Okay. All right, so we have a definite integral, so we're going to get a final answer of a number. So 0 to 1, e to the negative x, 2e to the negative x plus 3 to the 9th dx. Now, this ninth power is kind of what's tipping me off to what I might want to be u, because this is really, to try and multiply this out would be a huge mess. Oops. So I really want to try to simplify that. So I'm going to look at letting u be this inside piece right here. 2e to the negative x plus 3. Okay?
All right.
Because that'll simplify this down to u to the 9th. Now, we need to make sure we can get the du in, which is basically the derivative of this guy. Now, the derivative of an exponential is itself times the derivative of the exponent. That comes from our chain rule. So I know the du is 2e to the negative x times the derivative of negative x, which is negative 1. Derivative of 3 by itself is just 0. So I can put the dx on. Let's clean that up a little. And as I'm going through this, if you guys have questions, let me know. So now let's see about making our substitution. And I want to change colors for this because I just want to make this real obvious. So if I'm looking at this, I already know this part here is u. So that part I'm done with. This e to the negative x is going to come in handy because it's going to match up with that e to the negative x here. So that e to the negative x dx is going to be part of my substitution. The only thing missing is that negative 2. So I'm going to put the negative 2 in there because that there, hopefully this isn't getting too messy, that there is my du. Yes. What I need to, here's the way that I look at it. We get to choose u. So we do that, and then we calculate du. Then what I need is to make this be in my integrand so I can substitute in the du. Now, because I put that negative 2 in there, I've got to compensate for it outside with a negative 1/2, because now I haven't changed the original integral. So we've got the negative 1/2 out front. The negative 2e to the negative x dx is du. So we end up with u to the 9th du. This is nice because now we're down to a very basic antiderivative. Now, like I said, I like changing the limits, although they're not going to be very pretty on this one no matter what we do. Because if x equals 0, we have 2e to the negative 0 plus 3. E to the negative 0 is 1 times 2 is 2 plus 3 is 5. So that's our new lower limit. And then this one, not much we can do. When x is 1, that's our upper limit. It's not pretty, but it does save us having to sub back. And now I only have to focus on the antiderivative in red. I'm done with what's up in the purple. So negative 1/2. Antiderivative of u to the 9th is u to the 10th over 10. And that's going to go from 5 to 2e to the minus 1 plus 3. We can multiply these together to make it a little cleaner, make that a negative 1/20th. And then we'll plug in our limits into the 10th power. So 2e to the minus 1 plus 3 to the 10th minus 5 to the 10th. And because this is going to be a mess no matter what we do, I'm just going to leave it like this. This is a nice exact answer. It's not pretty, but it's exact. If we wanted to get the decimal approximation, we could put that into a calculator or a Wolfram, but this is perfectly fine for a final answer.